So now let's look at the details, right? Let's start with clustering, and yeah, first of all, a recap as promised, and then two new things, so to say, which I wanted to show you, which are the mean shift algorithm and spectral clustering. Actually, both are quite popular in different domains, so and sometimes also quite valuable. And you probably know that clustering is mostly, since it's unsupervised, you don't exactly know what should be the outcome. So clustering is always a kind of puzzle game. Yeah, so you apply a lot of different clustering algorithms, and all of those clustering algorithms tell you something about the bigger picture. And the more methods you have at hand that you can apply, and that you know what those methods actually give you, what part of the big picture they give you, is the better. Yeah, so that's why I wanted to introduce also those two things here. Anyway, let's start with the recap. So I just said that clustering is unsupervised, and the patterns that we look for are groups of similar objects, the clusters. And there are different ways to actually define what a clustering is, or what a cluster is. For example, like k-means does it, and EM does it, for example. We could look for groups of objects that minimize intra-cluster distances. So pairwise in-between cluster distances should be small. So similarity within the cluster should be high, compact clusters. And simultaneously maybe also maximizing inter-cluster distances. So similarity or distances between clusters, pairs of points from different clusters should be high, distances high, similarity low, of course. Yeah, similar distance measure is important, for example, of course, in that case, but that's how it is. The question is how to actually define what a cluster is actually, or what the characteristics of these patterns, these clusters are. So how do the patterns look like? That is somehow the first implicit assumption when you actually choose a given algorithm, because each algorithm actually defines the patterns or the characteristics of the patterns a little bit different, and then basically search for that specific patterns. And sometimes they find it because it's there, sometimes they don't find it. Some algorithms actually give you results anyway, like k-means gives you k clusters all the time, even though there are no real specific clusters in there. So that is the puzzle playing game I told you before. And I like to show students, people, whatever, when we talk about clustering, these different data sets, where you see, okay, this is a data set, this is the data set, this is a data set, this is a data set. Well, just looking at it, because it's two-dimensional, you probably have, for all those four different four different data sets, different ideas, or clear ideas actually, how the clusters look like, what the clusters are actually. So here we have maybe 3 clusters in this one here. Here we may have 1, 2, 3, maybe a fourth one, or is that noise? I don't know. Here we have probably also 4, 1, but they look completely different than here. They are not spherical, but they have some arbitrary shape. And here we have maybe nested clustering structure, so one bigger cluster, and nested within this bigger cluster we have 3 more specific clusters embedded in this bigger one, and stuff like that. So there are many different patterns that we could intuitively somehow define or interpret as clusters. And different algorithms basically look for different patterns. So partitioning algorithms, for example, look for those spherical clusters. They have no chance even to get those clusters here. But density-based clustering algorithms like dbScan and stuff would detect those parts here. And they are not probably so good when density levels are different and stuff like that, and hierarchical structures are present. Here we need hierarchical clustering algorithms and stuff like that. So whatever I'm talking about, for those who have no clue, it's about the point that clustering is puzzle playing, yeah, and each clustering algorithm actually looks for different patterns, looking completely different. So the result of each clustering algorithm actually gives you some puzzle piece for the bigger picture. Since you don't know what's in there, it's somehow a kind of exploratory puzzle playing game. Yeah. So yeah, but it's not puzzle playing game, or it's not called puzzle, but it's called clustering. Yeah, but that's just the difference. So some general considerations, which I probably already told you, but once again, so unsupervised, we have no clue about the characteristics of the clusters. We don't know if they are looking like this, like this, or like this, especially if the data is high dimensional, of course. Yeah, if it's two dimensional, we just plot it and have a look, of course. Yeah, like this one here. But in general, we cannot plot it. We have no clue about the characteristics of the underlying patterns. We don't know how many are there. We don't know about the data distribution they have. We don't know what shape do they have, and we also do not know what is their noise, yeah, like here and here, or don't we have any noise, which is typically not the case in real applications. But anyway, yeah. And that's what I said. Clustering methods usually make a lot of assumptions regarding those questions, especially about the data distribution and the shape of the clusters, and sometimes also on how many clusters there are. Yeah? And what I just said already, typically a particular method assumes a given pattern, the so-called cluster model, which is defined implicitly or by some input parameters or both. Yeah? And then the methods basically search for those patterns and nothing else typically. Yeah? So you just get the information from these methods. Is this pattern there or not? Yeah, but not necessarily that is the only pattern. Yeah, so always keep this in mind and always be very careful about the results of clustering algorithms. Think about the analogy or the intuition of a puzzle game. So here are some different paradigms, clustering models. Yeah, so that is about the distribution of the patterns, the data distribution of the patterns, the shape of the patterns, maybe also about the number of the patterns. Yeah, the different clustering models, the different algorithms, just vary in those regards. Yeah, so here's one of the most well-known paradigm, well-known clustering model, which is generally called partitioning model. So k-means, k-medoid, maybe you know it, are partitioning methods. And the basic idea of those methods following this model is to construct k partitions. Yeah? K is the only input parameter, so k is the number of patterns, the number of clusters, which needs to be given as a parameter. And the partitions are typically spherical, like spheres. Yeah? These partitions are optimal with respect to some cluster criterion, for example, compactness or coherence or something like that. Yeah? Popular methods are, for example, k-means or k-medoid, just talking about that. And the most important concepts for those things here are, well, we represent clusters by some specific prototype, so to say. With k-means, it's the mean of the members of the cluster. Medoid is another prototype of a set of points, representing a set of points. A cluster is a set of points, so those are prototypes to represent the number, a set of points. Yeah, mean, medoid, median, mode for categorical data, and so on and so on. You can think of any variant here. And we need, of course, a cluster criterion, for example, compactness, yeah, like the sum of the squared distances to the representatives. And you probably know the basic algorithmic schema. If not, then just look it up or look the details a little bit more up in the textbook. So at start, we start, for example, if we look for two clusters, k, the input parameter is set to 2. So we look for two clusters. We start with two initial randomly chosen cluster representatives. For example, this one here for the first cluster and this one here for the second cluster. And then we start to assign each point to the closest representative. Like these guys here are assigned to the green one, and those guys here are assigned to the orange one. And then we update the cluster representative. So if we use the mean, we compute the mean of the green points, which is this one here. And then we compute also the mean of the orange points, which is probably this one here. And then again, we have to reassign the points to the closest cluster representative. So this guy originally belonged to this one here, but now it belongs to this one here because this cluster representative is more closely to this one here than this one here. Yeah. So we reassign the points to the closest cluster center, update the cluster center, so we recompute the means of the two sets, and then again reassign the points to the closest one, to the closest cluster center, and so on and so on. And most of you know that at some point in time, all the points are again assigned to the same cluster center as before. So the update ends up in actually no change, and at this point the algorithm actually converges and stops. Yeah? And we have our clusters found, which are represented by the representative objects, means, mediates, whatever it is.